Okay, so this is just going to be a review of fluids. This is going to be a really quick review. We're probably going to try to cover a lot, but we need to review for your test tomorrow. So let's talk about, remember, a fluid is incompressible, which means its density does not change. And if you are underneath or submerged in a fluid, here's a regular object, there you go, looks like a popcorn kernel or something, then you're going to have pressure exerting a force on all sides, and that's due to the fact that you have those little tiny molecules or atoms or whatever hitting you on all sides. But we also know that as you go down in the fluid, the pressure is going to increase. So that means these guys down here are actually hitting more often or harder, and so there's more pressure, more force on the underside than what there is on the top of the object, and so that gives you a net buoyant force. So the buoyant force has to do with the density of the fluid, the gravity, and this of the fluid, that is an F, yep, and then the volume of the fluid that's being displaced. So it's not the volume of the object. Now, if the object is submerged, then the volume of the object equals the volume of the fluid that's being displaced. But if you have an object, say up here, that is only partially submerged, then you don't know what the volume of the object might be. All you know is that the volume of the object, or the water being displaced, is less than the volume of the object. But if we're talking about submerged or floating, an object that is floating in a fluid, so that's floating here, we know that the buoyant force also has to equal the gravitational weight of the object itself, and that is just mass of the object times gravity. Okay, if we know that an object is sinking, is underneath the water, then we know the buoyant force is less than the weight of the actual object. But we can calculate the buoyant force as being the density of the fluid, gravity, and the volume of the fluid being displaced. Okay. So if something is inside the fluid, completely submerged, maybe hanging from a string or something like that, then we know that the buoyant force is got to be mixing with the gravitational weight and the tension in the string so that everything kind of comes out equal. You could also be doing this with something that is wanting to float, okay, yeah, wanting to float, but is being held down by a string. Okay, in this case, again, the buoyant force would have to be greater than the weight, but we have some tension that's also in there. So in this case, the buoyant force would have to equal the weight of the object plus the tension, because you have tension going down, you have weight going down, and you have buoyant force going up. So this is a lot of Newton's second law stuff in these force equations that we're dealing with. It's just that the buoyant force is always due to the water being displaced, not of the volume of the object itself, unless it's completely underwater, like we've said before. Now we've also figured out that if you start moving a fluid through a pipe, okay, then you constrict that pipe to some smaller degree. The same volume of water that has to move through this pipe has to move through this pipe as well, and so it has to travel a much farther distance. Therefore, your velocity your velocity is going to increase. So the velocity over here, if this is 2 and it's 1, velocity 2 is less than velocity 1. Okay. We also have figured out that if you increase the velocity, you have to steal that kinetic energy from someplace, and so your pressure is going to go down. So if we're talking about pressure, P1, P2, P2 is bigger than P1. So as velocity goes up, pressure goes down. And then this is where we kind of got the continuity equation. This is the A1 V1 equals A2 V2. Continuity equation just means that the volume of water that goes through one side has to go through the other side. That's all it means. This is a nice ratio equation, so if this happens to be twice the size as this side over here, then that means it's going to have half of the velocity. 3 times would be 1/3, and yada yada yada. You get the idea. because it's a ratio equation, we don't necessarily have to get out of different units, so we don't have to work in meters. If both of the areas are in centimeters squared, then it works just fine. Okay, but how do we figure out what those pressures are? Well, this is where we get Bernoulli's equation, right? And Bernoulli's equation is P1 not P equals P1 plus 1/2 rho V1 squared plus, that's a rho. Wow. Okay, rho V1 squared plus rho GH1 equals the same thing, P2 plus 1/2 rho V2 squared plus rho GH2. Just the same thing somewhere else. So this is all this is energy, right? This is saying that the energy in one place is equal to the total energy in the other place. That's all that is. So we think about all the different energies that we have. We got potential energy, we got a kinetic energy, we got this internal thing that acts like energy that we call pressure. That's energy per unit volume. So if we're looking at, let's say, the last problem that we were working in class, so this is the 2009 B3 problem, where you got a pipe that comes up, it does constrict, and we have water that's shooting out at the end. We know that the area of the pipe, let's see what, underground, the area is 1 times 10 to the negative 4th meter squared. Here, the area is 0.5 times 10 to the negative 4th meter squared. We also know that the water is coming out with a speed of 8.2 meters per second, and the first thing says calculate the velocity down here at the bottom of the pipe. Well, this is just continuity, right? We got all the different areas and stuff. Volume that goes through the bottom has to go through the top. So A1 V1 equals A2 V2. You know, we can make a mention here that if you notice, the area at the top is actually half of the area at the bottom, right? So that means if we call this side 1 and this side 2, that means A2 is 1/2 A1. That might make our life easier because see what happens. A1 V1 equals, now we're going to say 1/2 A1 V2. A1s actually cancel out. So V1 is equal to 1/2 of V2. Well, V2 is just 8.2. So if you do 1/2 of 8.2 meters per second, then you get 4.1 meters per second. Nice ratio. And that's the velocity of the water going through the bottom of the pipe. Okay, so now we're looking for pressure. Now it's actually asking for absolute pressure. So we have all this moving fluid, we have a change in height, so it's going to be Bernoulli's. So pressure at the bottom plus 1/2 rho V bottom squared plus rho G H at the bottom equals 1/2, pressure at the top plus 1/2 rho V T squared plus rho G HT, or H2, no, T. Okay, so I'll go back to the drawing here for a second. If we talk about height, then maybe we call this level H equals 0, and that means this level down here is H equals a negative 0.5 meters. Why is it negative? Because it's down below. So that means the top H is 0, that thing goes away. We actually know that the pressure at the top is just atmospheric pressure. This is ATM pressure. Now that's important because we're asked for absolute pressure. Remember, absolute pressure and gauge pressure are two different things. Gauge pressure is just what it is underneath the water. Absolute pressure is adding the atmosphere on top of that. So there's our atmosphere. So if we're looking for this, that would be our absolute pressure because we have atmospheric pressure on the other side. And let's rearrange things. I'm going to do all the algebra in one step here. Pressure at the bottom is equal to atmospheric pressure, which is the pressure at the top, plus 1/2 rho, and I'm going to factor out some things, VT squared minus VB squared, and then minus rho GH at the bottom. Notice that we have a minus sign here, but our height is going to be a negative number, so when you actually plug this in, it's going to be adding over here on this side. It will be an addition. If you plug in all of the information here, then you're going to get a pressure at the bottom of 1.3 times 10 to the 5th pascals. You have to make sure you put atmospheric pressure in pascals, not just using 1 atmosphere. So this is the final answer for that. Okay, make sure that you understand how the algebra worked out, and make sure you understand the values. I would definitely plug this into the calculator yourself to make sure you got it, and go on about your business there. The last part, part C, is saying, okay, we have this opening, we have water coming out of it, okay, and all going all directions. What if it goes straight up in the air? How far up does it go? Well, we know it's coming out with a velocity of 8.2 meters per second. What is the velocity when it gets all the way up to the top? Well, it stops to come back around, so that means it's 0 meters per second. We know that the acceleration this entire time is the acceleration due to gravity, and this just hopefully looks like a kinematics problem for you. And what equation we would use? Well, we don't have time, so it's the only one that doesn't have time in it. That's v squared equals vo squared plus 2a x. Now your equation sheet looks a little bit differently. It says x minus xo in there, but we usually take xo to be our starting position, which is 0, so that thing goes away. So if you solve this for x, again doing all the algebra here, it's v squared minus vo squared over 2a, plugging all the information in, you get 3.43 meters. Again, I would do the algebra yourself. I would plug in everything into the calculator yourself so that you understand where I got that number. Alright, so this is a really quick review of all the stuff that we did, plus going over that last problem. The test will be fully AP, but the AP problems that I pick out are similar in nature to the ones that we've been working in class. If you have any questions, let me know.